had started the basics of linear algebra, and today and this week we'll complete the rest of the linear algebra that is required for this course. And that is not just required for this course, but also probably required for machine learning. So whatever machine learning you need to know, whatever algebra is required for machine learning, we'll probably cover most of it in this class, in this week, and in the previous lecture. So that should be good word for optimization in machine learning. And we'll also cover, along with this, we'll also cover, so today or this week, we'll also try to cover some calculus, basically vector calculus, where you'll learn how to deal with a vector valued function, take its gradient, take its Hessian, the properties of Hessian, and where are they used. They'll be used mostly in understanding, in deriving your gradient based algorithms that are, gradient is key to optimization, and gradient of a vector valued function is something that is not trivial to calculate or compute. And not just gradient, the double derivative, which is the Hessian, which leads to a matrix, and something that we will learn in this class. And that matrix has a very special property at times. And if that matrix, that Hessian matrix, satisfies that property, then the function is convex, etc. So the ideas that we are going to develop today and that we will take to calculus will be very useful for a lot of stuff that is done around optimization for machine learning. So that's the overall overview of this week's classes. Okay. All right. So let me just go to my screen and well, I hope I. So if you recall, in the previous class, we were looking at matrix. We said that any matrix A can be written as C into R. That was one of the main outcomes of the previous class. And this C matrix actually contained the columns of A, right? And R matrix contained the linear combination of columns of A required. So let's say if I have Ck, right, K columns of A, then R contains the linear combination of these columns such that I get my matrix A, right? So this was for the first decomposition. The question I have for you is that is this the only decomposition of the matrix A? Is my question clear? So is this the only decomposition of our matrix A? And even before this question is asked, let me ask you even a simpler question. Let's say I have this matrix. Let me just write this matrix: 1, 2, 3, 5, 4, 7, 2, 1, 3. Right? Okay. So can anybody tell me the rank of this matrix? What is the rank of A? So this is A. What is the rank of A? Hi, good morning, guys.
Yes, sir, 3.
3, okay. Anybody, Divanshu?
Yes, sir, it should be 3.
3. Shreya Srinivasan, 3. It's 2?
It's 3.
It's 3, okay. So yeah, the rank of this matrix is 3. I mean, it's clear, right, that all the columns are none of the columns are dependent on the rest of the column. That means I can't write the other columns as the linear combination of any other column. Okay, rest of the columns. So rank is 3, and I hope all of you see. Those who can't see, I'd like to ask them to go back and check this out. It's not trivially to prove, just by looking at the columns, that the rank is 3. So let's just say that the rank is indeed 3. So my question to you is, second question to you is, can I write can I write any point in R3? What's the point in R3? Like an X, Y, Z, right? Can I write any point R3 as linear combination of A, columns of A? So let's say I take this point 1, 1, 1. Can I write 1, 1, 1 as linear combination of columns of A? Palak?
Yes, sir.
I can. Why?
Uh, Sir, because I mean if we write it according, sir, can you give me just 5 minutes because I just woke up. I just need to get back. Just 5 minutes.
Yeah, you can.
Yeah,
You can go back and
just
wake
need
up,
to.
wake up
Yeah,
again.
sir,
All
just
right,
to, yeah.
that's okay. Anybody else? Anybody else? Yeah, Orko.
These are three independent vectors, so there will exist some combination that will result in a three-dimensional point.
Yeah, actually, the answer is the following: that when I do A into X, right, then I get Y. Y is a vector of dimension 3, right? Now, X contains nothing but the linear combinations of the column of A, and because the dimension of column space of A is what? What is the dimension of column space of A? Raidu?
3.
Yes, Raidu? Zubair? What is the column space dimension of column space of A?
Sir, 3.
3, right? Because the dimensions of the column space of A is 3, which means what? Which means what? See, I'm asking more questions because this is just, like a morning time, and I just want you guys to wake up before I really get into the flow of teaching. Okay? Robin, would you like to take a stab at this question?
Sir, can you repeat that?
So the question is that what is the dimension of column space of A? That's the first question.
Dimension of column space of A.
Yeah.
It's probably that is 3.
That is 3, right? And because the dimension of column space of thanks, Robin. Because the dimension of column space of A is 3, therefore when I take the linear combination of Robin, you can unmute now. I can if I take the linear combination of columns of A, then I get a vector of dimension 3, which is exactly what R3 is, and which means that I can actually get any point in R3, any Y in R3 by linearly combining columns of A, right? That's the answer. Okay.
Excuse me, sir.
Yeah.
Even if my rank of A would have been 2, let's say only 2 of them were linearly independent. In that case, also I can get any vector of R3, right?
Can you tell me why? In fact, if you recall the question that we had taken an example where all the vectors in A were identical, and actually I could not get every vector in R3 there, right?
Yeah, because that 1 1 1 3 3 5 5 5.
Yeah. So they were only in one line. They were not in the whole space, right?
Okay. So if let's say there are 3, that means one is kind of x-axis, another is y, and another one will be in z.
Yeah,
so we'll be able to get
exactly. Yeah,
Okay.
that's the way to understand it geometrically, right? Right, but algebraically, the way to understand is that it is not, because it is not spanning the whole space. You can't get every point of the space. Okay.
Yeah.
So, okay, let me just continue with where Rohit has left. Can you give me another matrix A? Very simple question. Palak, are you awake now?
Yes, sir.
Okay. Can you, Palak, give me another matrix A that from where you can generate all the elements in R3?
So we can do the row form now, because right now we do the column format. We can.
Another matrix A. Give me another matrix A. Either row, column, whatever.
I mean,
So-
a new example you're asking for?
New example of A. Yeah. Yeah.
Yeah, so we can go for 1, 3, 4.
Give me the simplest matrix A. Okay, let's just say that. Simplest. Ekdam easy matrix though.
So the identity matrix.
Identity matrix. Yeah, exactly. 1 0 0 0 0 1. Sorry, 0 1 0
0, 1,
and
0.
0 0 1. Right? So this is also another matrix A. Okay, which is also the identity matrix A. Identity matrix I, sorry. Another matrix A that I can use to generate any element in R3. I hope nobody has a question in this one. This is clear, right? You see, basically all my coordinates. Yeah, Siraj, question?
Sir, I'm saying that in the like when A was 1, 2, 3, 5, 4, 7. So we said that the column space of A is the entire R3. So I'm asking that if A is a 4 cross 4 matrix, then if the rank of A is like, then how will we prove, like I wanted to ask that how are we saying that the column space of A is entire R3 just because we have 3 basis vectors, that is why, or is there some other reason?
I mean, just because there are 3 basis vectors is not the only thing, right? That you understand?
Okay.
So how do we prove that? We'll come to that.
Okay.
Okay. We have not proved it yet. I mean, it's very easy to see, but we have not proved it yet.
So that if there's a 4 cross 4 vector, 4 cross 4 matrix, and we have 4 basis vectors, so then can we say that the column space of that matrix will be the complete R4?
If all the 4 are linearly independent, yes.
Okay, sir. Thank you.
Yeah. Yeah.
Okay.
Okay. So yeah. So I see the point is that we are not doing the whole course on linear algebra, so I can't get into the definitions, mathematical definitions, and their theorems and the corollaries of those theorems, and we have to little bit rush through all these things. So I'm just trying to give you the intuitive sense of what what is important and what is not important. So what is important to hear in this case, or what is the crux of the whole discussion, is that columns of A contains basis, and again we have not deliberated on basis with a lot of detail, but what we want to say is that columns of A contains the basis of a space, of a vector space. Okay, that we have proved that it's a vector space. Now we are just trying to take it one more step ahead, and we are saying that the columns of A contains the basis of some vector space, and using that as basis, we can actually derive any element of that space. Right? This is the only idea I want to give you. Okay, but the question is that are these columns the only basis of the vector space that is spanned by the columns of A? The answer is no. Right? So you see, I said that this matrix A, actually you can derive using this matrix A every element of R3, but you can also derive. So this is my matrix number 1, right? And this is my matrix number 2. You can also derive the same elements, okay, by using this matrix also, which means that I can use some other matrix also to derive the elements of the same space, same set. All right. Of course, it will have a different linear combination, but I can have different matrix also with the same space. That is the only point I'm trying to make, which means that I can decompose my matrix not just in one way, not just in, that's where the discussion started, right? I don't have to just take columns of A to decompose my matrix. I can take some other columns also, okay, some other matrix also, and decompose that matrix as product of 2 other matrices. And that is the whole point we are trying to make. We are trying to understand how can we decompose a matrix A. In fact, I think I've forgotten one thing here. I wanted to talk about 4 subspaces. We'll do that now. So, the idea is that we can decompose our data matrix A, now I'm coming to the machine learning and the data part of it, will have a very, very fat matrix with lots of columns and some rows, let's say 1 million columns and 1,000 rows. And I don't have to decompose that, that matrix, which is, let's say, of dimension 100 cross 100,000 as the columns of A, but I can also take some other columns, okay, some other set of columns, and decompose this data matrix into those, let's say, those X into Y, where X do not necessarily contain the columns of A, but some other columns, some other matrix times Y. Okay, and this is exactly what your whole ML and data is all about, where you want to find the best representation of your data. Okay, this is nothing but a representation of your data, right? So A is a matrix, C into R is the same matrix. Okay, similarly, this is my matrix, this will be your data matrix, and X into Y is some other set of matrices, and this is nothing but the representation of your data into or decomposition of your data into product of two matrices X and Y, where X and Y may have a different meaning, may have a total different sense altogether, and that is important for your problem. For example, you may also say that, hey, I don't want exact decomposition, I want the most approximate or most accurate decomposition which contains only 10 columns, let's say, right? So I have 100 plus 10,000 matrix or 100,000 matrix, and I want to decompose that into, let's say, 100 cross 10 times 10 cross 10,000, right? What is that matrix which is closest to A that contains only 10 columns? Now that matrix is not that X is not the any 10 columns, linearly independent columns of A times Y. No. Okay, that X could be something else. Are you getting the question? I hope this is clear, right? That the decomposition may not be done only using the columns of A, but you can have some other matrix also. And I'm trying to motivate that by this case. I'm saying that, hey, remember, even this matrix A, that black circled matrix A, spanned certain space, but the elements of that space could also have been written as a linear combination of some other columns which are not of A. Yet I can get the same thing, and we will extend the same idea. Okay, this is the crux of the discussion. I hope this is clear. If anybody has a question, you can ask. Then I will. Otherwise, I'll go and quickly do something very, very. We'll just basically extend the same thing into different decompositions. Okay. All right, great. So this is the. I mean, I hope everybody is now awake, and we already spent like 10-15 minutes on this. So I want to just finish the discussion with two things. One is discussion on more subspaces. So there are 4 fundamental subspaces. We have already seen one subspace. We'll look at 3 other subspaces very quickly and move to what is called as eigenvalue decomposition. Basically decomposing our matrix into what is called as the set of eigenvectors. So the columns of C will be now eigenvectors, right? So to understand those eigenvectors, we'll have to understand some 4 subspaces that are fundamental subspaces, right? So the first subspace is, NA, or the column space of A. We have already seen this subspace, right? We know what is the column space of A. Nobody has a question here? Okay. Now the second subspace, actually, I'm sorry, this is CA, not NA. I jumped the gun. There's another subspace called NA, or null space of A. What is the null space of A? Anybody? Yeah, Rohan?
So it's basically all X such that AX is equal to 0.
That's right. So suppose A is a M cross N matrix. Okay. Let's say A is a N cross N matrix. Then let me ask somebody. Who should I ask? Or anybody can answer. Tell me the dimension of each element of column space of A. Amisha? What is the
Yes,
dimension
sir.
of each element of column space of A?
It will be M cross 1.
M cross 1, column space of A, right?
Oh, column space. I thought you said column. Okay.
Columns, what is the element of, no, actually you did give the right answer. What is the dimension, what is the vector length of each element of column space of A?
I mean, length of each column would be M, right?
So if I have, ठीक है Misha, thanks. If I have A is M cross N, right? This is M cross N, N elements, N columns. Then the column space of A is basically all. What is column space of A?
Number of linearly independent columns of A.
No, that's not column space of A. That is the dimension of the column space of A. What is the column space of A?
So the linear combinations of all those linearly independent columns, the
Yes.
vector space they make.
Yes, yes. So y is equal to AX. So y is the elements, y is the column space of A, which is of what? Length M, right? Because this is N cross 1. Therefore, y is M cross 1. Isn't it? So that's the column space of A. Okay? You understand the point, right? So basically, every element of the column space is a vector of length M, right? Now, this is column space. What is null space of A? Null space of A is defined as the following. Okay, this is also a set, right? Also a set of all vectors x such that AX is equal to 0. Okay, so column space of A is the final product of linear combinations of the columns of A. Null space of A are those vectors that when you linearly combine them with columns of A, it gives 0. It gives a null vector. Okay, a 0 vector. Okay, so what is the dimension of X in this case?
N cross 1.
N cross 1, right? So this is N cross 1. Okay, so this is a very, very important point to understand. This is very crucial difference to understand that if A is not a square matrix, then the element of column space and element of null space have different dimensions. Okay, so first of all, question to you. Can you prove that? Can you just write in your copies, prove that null space of A is a vector space? Can you convince yourself? Is null space of a vector space? Again, right? Null space of every vector space is a set. Okay. In this case, this set, and every set has a membership rule to that club, right? What is the membership rule here? The membership rule is AX is equal to 0. Yes, Shantika?
Yes, sir. If say u belongs to x, so a into u also equals to 0, and v is another one vector
Mhm.
belongs to x, so a into v is always also equals to 0. So we can sum this to, I mean, a into u plus a into v, so that is equals to 0. So and if I multiply a into, I mean, with some scalar, so that is also equals to 0. So we can say that the null space is a vector space because it satisfies both addition and multiplication property.
That's right. Okay. Anybody has a question on this explanation by Shantika? Why is null space a vector space? Right? Because it satisfies the two properties that vector space should satisfy. The first property is closure under addition, and the second property is closure under scalar multiplication, right? So null space is also a vector space, which also means that null space should have a dimension, right? Every vector space has a dimension. Okay, so can you talk about the dimension of null space of A? Okay, here's a question to you. Tell me the dimension of null space of this. this matrix. So this is my example, right? Let's call this matrix as B. What is the dimension of null space of B? Ananya?
Yes, sir. So it should be 3.
Dimension of null space of B is 3. Okay, fine. Debarshi?
Sir, sir, it will be like null space of V will be first like the uh, mm, values of B for which it will be multiplied with 0. So,
Okay.
so
Okay, let's ask Ananya why is it 3? Ananya, why is it 3?
So basically, how we've defined a null space is that it is all the x for which ax is 0. So since we can see that A is of rank 3, or it has 3 linearly independent columns, so
Columns.
x would definitely be a 3 dimension.
What is the meaning of, okay, no, let's press on this further then. What is the meaning of linear independence of columns of A?
sir means each of the
Wait, Debarshi, wait. I want to press Ananya here. Ananya.
Yes, sir. So basically, linear independence would be that, I mean, there is, we can't represent like a third column with the help of like 2 other column, or any linear combination of 2 other columns. So like each column is linearly independent.
So if each column is, if all the columns are linearly independent, which means that I can't have, is this correct that x1 c1 plus x2 c2 plus x3 c3 is equal to 0 implies x1 is equal to x2 is equal to x3 is equal to 0? So other than 0, 0, 0, there is no way
Yes.
I can write. You agree, right?
Right.
But then you're saying that there exists a vector x such that x1 c1 plus x2 c2 plus x3 c3 is equal to 0. That's the meaning of null space.
So
Are you
like
getting?
there can be another, yes, so there can be another, like it could be -1, 1 and 0.
So you are saying that there
X1,
exists
X2.
x1. Wait. So you are saying that there exists x1, x2, x3 such that when I take a linear combination, it will lead to 0, right?
Yes, sir.
Which means that they are not linearly independent. Right, Ananya?
Yes, sir.
So do you want to revise your answer now? So you're saying that they are linear, they are not linearly independent. These three columns that I've written are not Li. That's what you're saying now. Ananya.
Yes, sir.
Okay. Hinakshi.
Yes, sir.
Are they linearly independent?
Sir, linearly independence basically it has, if A is a matrix, then it should have a non-pivot row. So,
Okay, Dipanshu.
Yes, sir. So the elements, since the column vectors here are linearly independent, so the null space should be 0 because
Okay.
yeah.
Okay, we have got a new answer. Okay, Raidu. Yes, Raidu, go ahead.
Sir, I'm thinking it should be 1 as minimum.
Okay, we have got all the answers now. 3, 1, 0, 2 is left. Rohit, are you going to give 2?
Sir, it should be an empty set, right?
It should be an empty set. Okay, Shantika, you?
Or it can be all zeros.
Yes, sir, 0.
Okay, Rohan?
So I think the dimension of the null space is 0 since the only vector is the trivial case that is 0, 0, 0.
और
It's
को
the zero vector basically.
ठीक है और
I
को
actually have a question. Isn't 000 by itself also a vector space?
So no, so that is exactly what you exclude from the definition of vector space. So that's a trivial vector space, right? Vector space of one element.
Okay.
Right, so it's not even a vector space because there is just one element. So Ananya, would you like to change any of the answers that you have now that you have heard others? This is very basic question, right? We have seen this. Ananya,
Yes, sir.
what is the change now? Tell me.
So it should be empty set.
Why should it be empty set? Okay, कोई बात नहीं, ठीक है. So Ananya, you should go back and read a little bit more about linearly independent columns of A. Okay, or what is the meaning of linear independence? It's an empty set. It is an empty set indeed. Null space of A is an empty set, and it is an empty set because all the three columns are linearly independent, because you can't represent any of these against any remaining any of these. Okay, and because it is an empty set, therefore the null space of A contains no element other than 0, 0, 0, because what is the meaning of null space of A? Null space of A means all the vectors x such that Ax equal to 0. What is Ax equal to 0? Ax equal to 0 means linear combinations of columns of A, right, from the elements of x. Okay, the linear combination coefficients are the elements of x. Remember, we did that in the first class, that when I do A into x, I mean linearly combining the columns of A by the elements of x. But because I can't get any linear combination that will lead to 0, which means that there exists no x. There exists no x such that there is no such x other than 0, 0, 0, which means that null space of A contains only one element, 0, 0, 0. Other than that, there is no other element, right? That's it. Which means, null space of A has 0 dimension, basically. Okay? And why not? The column space of A has dimension 3, which means that, all the elements of R3, right, are available in the column space of this matrix B, not A, sorry, B. Actually, this is B. Okay, all the elements of this column space of B is basically contains it is R3. Therefore, there is no other element left from that set. So obviously, null set or the null space will have nothing, because everything from R3 has been taken by the column space of B. Right? Is this clear, guys? You see, the column space of B, in this case, the column space of B is R3, right? Basically is R3. Okay, so all the elements of the form XYZ has been taken by column space of B, so nothing is left for null space of B. Okay, so null space of B is basically just an empty set, right? Okay, I mean 0, 0, 0 does not count because it's a trivial answer. Okay, so it's an empty set. So this is clear, right? Okay.
Yes, sir.
Have you heard of what is called as the rank nullity theorem? Have you guys heard of this? Anybody has heard of this? अरे किसी ने क्या बिल्कुल भी लीनियर अलजेब्रा नहीं किया है क्या? Maybe we should have a full course on LA for you guys. And nobody has heard of rank nullity theorem? Okay.
So I have heard of it, but I don't remember it completely.
Okay. Can you guess what is the rank nullity theorem? I think we'll just spend like
maybe
4
Sir,
weeks on this.
is it like the sum of column space and null space is equal to the dimension of the matrix?
Dimension of the
No,
matrix.
the total rank of the matrix. Sorry, yeah.
Rank of the no. I mean, we
So
saw
I
right
think
that
the sum is the number of columns of the matrix.
sum is the number of columns of the matrix. Okay,
Yeah.
Rohan, can you just little bit explain this more for
Yes,
everybody?
sir. So basically, rank of a matrix is the number of linearly independent columns. And nullity, I guess the null space is the remaining column. So rank plus nullity of that is the total number of columns of the matrix.
That is almost right. Yes, Raidu.
Yeah, same sir. What he told. Dimension dimension minus rank equals null.
Okay. Yeah. So sort of that. I'm not going to go deeper. I want you guys to go back and check this out. Okay. Please go back and read what is the rank nullity theorem. Okay. Try to prove this also. What I'll do is the question set that I'm preparing for you guys, I'll just note it there. But the key, what is the key point that I want you guys to understand? The key point is the following: that if I have a m cross n matrix, right? So let's say I have 10 cross 100 matrix. Okay. Obviously, we saw that in the previous class that what is the maximum rank of this matrix?
10.
10, right? Maximum, right? It could actually be less than 10. Okay. But there are 100 columns. So obviously, remaining are not linearly independent, right? 90 columns, which you can represent as the remaining 10 columns. So what does that mean? It means that, because you can represent the remaining 90 by the linear combination of the 10, it means that there are so many vectors x, right? There are so many possible vectors x that you can use to linearly combine these columns and get a null, isn't it? Get a 0, right? Because you can combine, so let's just say that, the first 10 columns are the linearly independent columns, right? And the remaining 90 columns are dependent columns. Let's just say that. So these are the dependent columns and these are the independent columns. I mean, I'm just saying that these first 10 columns are independent. I don't mean to say that the remaining columns are not independent amongst each other. But let's say the first 10 columns are linearly independent, which means I can represent the remaining 90 columns as a linear combination of the first 10 columns, which means that, there'll be there'll be some vector, some values here, right? That will lead to 0, isn't it? Is this clear?
Yes, sir. Yes, sir.
Right? Because that is the case, which means that my null space is this, right? Null space is all the vectors, all such vectors, right? That will lead to 0. Okay? Which means that the null space exists and there are so many elements in the null space, right? Now, what is the dimension of the whole vector x? What is this dimension? So let's say this is my element, this is my matrix A, 10 cross 100 matrix A. What is the dimension of x? 100, right? So 100 is the dimension of x, which is also same as the number of columns of this matrix A. Okay. And because there are 10 linearly independent columns, therefore the dimension of the column space is 10, right? And the total number of columns are 100. Okay, so therefore the rank nullity theorem says that the dimension of the null space is 100 minus 10, which is 90. Right? So dono ko milake, they span, I mean, they are by the way, they are in different vector spaces. Okay. The column space, the size of the column space, the dimension of the column space is 10. Right? And the dimension of the null space, the prospective dimension of the null space is 100. But actually it won't be 100, it will be 90. Okay. That is what rank nullity theorem says. Why? Because when I linearly combine the columns, I am getting 0. And there are many such combinations possible, which means this is a set right? This is a set. Okay, remember I did I write null space? So this null space, therefore, is a proper set, and we have seen that this set is nothing but a vector space. Therefore, it has some dimension, right? Because it has some dimension. In this case, if the column space is of dimension 10, then the null space will be of dimension 90 using the rank nullity theorem. Now, we have not proved it. I'm just trying to give you an intuitive feel about it. I hope this is clear. I hope you have some intuition behind it. Robin, Ratan, any question on this?
Yeah, so this rank nullity theorem states that the linearly aside from the if the linearly independent columns are equal to the dimension of the whole are equal to the dimension of the column space of the matrix, then the null space would be zero, right? Essentially, if the rank is equal to the dimension of the matrix.
Yeah, the rank, no, the rank is equal to the dimension of the matrix could also be true for a non-square matrix. Okay.
Yeah.
So in this case, for example, this is a 10 cross 100 matrix. Okay. So the rank may be 10, but the number of columns are 100, right?
Yes. Yeah. So so only in the case where there is it is a only in the case where it is a square matrix can the rank maximum rank be can is there a possibility for null space to be zero, right? For in the
Yes.
only in the case of square matrix.
Yes.
And in all the other cases, there would be some vector space. There would be some vector space which, when combined with this matrix, will
No,
add up to zero.
not really. Sorry, not really, Robin. If I have a fat matrix, then yes. But if I have a tall matrix, then the number of columns will actually be very small. In that case, the dimension. In that case, also, the null space could be zero. Okay.
Okay.
So what is a tall matrix? Tall matrix is like this, right?
Yeah.
So very few columns and many rows. There also, the dimension of null space could be zero.
Okay. So here also rank can be defined by rank if this tall matrix has m cross n, m is greater than n. So the here rank can also potentially be m, right? Can rank can also be m here?
No, rank cannot be m here because rank is always less than or equal to the number of dimensions, basically either the number of columns or the number of rows. So rank cannot be equal to m here. Rank is always less than either the number of columns or the number of rows. This is exactly what we had done in the previous week. So I request you to go back and check those videos. Okay.
Okay.
Yeah. So guys, the idea that I want to drill here is that look at your matrix as from two angles. The first angle is the angle of the column space. Okay, column space, right? And the second angle is the angle of null space. And when you look at these two angles, you have sort of characterized the spaces in which this matrix operates pretty much. I mean, there are two other spaces also, but they're very similar spaces than these. Okay. Siraj, any question?
No, sir. Sir, I'm just a bit so I know that the vector length of that null space would be 100 if we are considering that 10
vector
cross
length
100.
of vector length is 100.
Yeah.
Yes.
So I guess I've also been using that dimension and that length, so that part is a bit.
Yeah. No, you don't, right? I mean, if I give you 5 points in one line, those points are in R3. Is the dimension of that space 3?
No, sir. It will be 1, but it will be in R3. Okay.
Right?
Okay, sir.
So confusion is clear now?
Yes, sir.
See, the question that Siraj is asking is following, that look, this X is of 100 dimension. Basically, X lies in R100. Right, Siraj? That's what you're saying?
Yes, sir.
But the null space may not be of dimension 100. The null space is of dimension 90.
90.
Right? So your vector space, element of the vector space could have 100 dimension vectors, but each point could be of 100 dimension, but the vector space, vectors, the dimension of the vector space could be less than 100. In this case, it may be 90. It is 90. That's how we've defined it. Right? Okay. On the other hand, I mean, one thing that people get always confused about always is that null space and the column space, as if they are sitting in the same bigger subspace. No, they are not. They may not be. In this case, the null space is in dimension 100 and the column space is in dimension 10. So they are two entirely different vector spaces of different dimensions. Okay, even every element of these vector spaces have different dimensions. The dimension of null space is 100 and the dimension of column space is 10. It's not 100. Right? The size of every vector of column space is not 100. The size of every vector of column space is 10. So this is something that you should really understand very well. Okay? Okay, I'm very I want to ask you at least one or two questions here, which I'm not able to ask because of the lack of time. Okay, but let's complete this argument completely, and then let's move on to what we call as eigenvalue decomposition. Okay, so we saw null space of A, we saw column space of A. Similarly, we can define column space of A transpose and null space of A transpose. Can you guys quickly tell me what is column space of A transpose here? What is column space of A transpose?
So it's nothing but the row space.
Sir, N.
N. Sorry, what is N?
So A is M cross N. So the dimension of, the column space of A transpose is N.
No, it could be anything. What is the definition? What is column space of A transpose? Well, what is A transpose? So if this is my A, then A transpose is this, right? So column space, the column space of A transpose is nothing but the number of linearly independent columns and of A transpose, which is the same as the number of rows of A, linearly independent rows of A, okay, and the space defined by those linearly independent rows. Is that okay? So, A transpose is nothing but the rows of A in columns, in the columns form, right? It's the same thing. Okay. So here is what I want to ask you. Okay, take some matrix A. Let's say I'm giving you a matrix A. Let's say this is the A matrix. Let me find this matrix A, 3 minus 6 minus 6. Yeah, this is a simple matrix, right? So you have to write all the 4 dimensions: NA, CA transpose, NA transpose. Write the dimension of all these 4 vector spaces. Okay, take a couple of minutes and do that. I'll take a break of I'll just take a water break, etc., and come back. Okay, so what you have to do is you have to write the dimension of null space of A, the dimension of column space of A, the dimension of column space of A transpose, and dimension of null space of A transpose. Okay, guys. So I'm ready to hear your answers. Nazreen Shah, Moksh, you have not spoken.
Sir? Yeah, so the column space of A is 1, null space of A is 2, column space of A transpose is 1, null space of A
Wait. Column space is 1. Okay. Null space is 2. Okay.
Column space of A transpose is 1. Null space of A transpose is 1.
Null space of A transpose is also 1.
Yes.
Okay. ठीक है. Moksh.
Yes, sir. Column space of A will be 1 and A transpose will also be 1.
Okay. Why is column space of A 1, Moksh?
Because only one column is linearly independent.
ठीक है. Okay. Okay. Who else would like to answer? Tanisha, you have not spoken.
Yes, sir. So the column space would be 1 and the column space of AT would also be 1. The null space would be 2. The null space of A transpose would be 1. Would be 1.
So, okay, fine. ठीक है. Anybody else? Vishal Kumar?
Yes, sir.
Explain why is column space of A transpose 1?
Sir, we'll take the transpose of A and then find the row echelon form to get the column space, like to get the rank.
Row echelon form. Okay. Yeah, Siraj.
So we can say that the column rank is always equal to the row rank, and we know that column A of column rank of A transpose will be row space of A, and which is equal to like without even calculating, we can directly say that if dimensions of column space of A is 1, then dimensions of column space of A transpose will also be 1.
Okay. Is that correct, Zubair?
Yes, sir. I mean, dimension of column space of A transpose is nothing but the dimension of row space of A. So we know that rank of column space is same as rank of row space. So that's why.
Okay. ठीक है. Chalo. So at least there is some understanding of this. Ananya, are you convinced about these numbers?
Yes, sir.
Okay. ठीक है. So, okay, let me just finally, I'm just tempted to ask just a couple of more simple questions. Okay. And don't have to prove right now, but you'll go back and prove it in your homes. So, question: can you comment on whether rank of two matrices, multiplication of two matrices AB and rank of A? Okay, so my question is, if I have two matrices AB, any matrices AB, okay, what is the relation of rank of this multiplication of AB with the rank of A? Think about it, right? Think for a minute, and then we can talk again. Will it be smaller than rank of A? Will it be equal to rank of A? Will it be greater than rank of A? Will it be less than equal to, greater than equal to? Obviously, you can't have greater than, less than both at the same time. Sorry. What about this? Similarly,
Sir,
Palak.
rank of AB will be less than equal to rank of A.
Less than equal to. What about rank of B?
Sir, I'll give it a thought.
Sir, less than or equal to minimum of rank of A, rank of B.
Wow, Zubair, I think you need to explain this.
Sir, I don't know the proof, but I have studied in the previous courses, sir. They didn't have the proof, sir.
Aren't you a PhD student, Zubair?
Yes, sir. Yes, sir.
Yeah. So, such stuff from PhD students should not come out. Even if you don't know the proof, just say that I don't know the proof. Don't say that this is what I know. Right?
Sure, sir.
Which means you're relying on your memory and not on your understanding. Anybody else?
So it will be less than rank of A only.
What about rank of B?
So same, sir, because AB is nothing but the when we like multiply AB, so AB is nothing but linear combination of columns of A. So
Okay.
dimension. So that's how I can say ki rank of AB will be less than or equal to rank of A.
Okay. What about rank of B?
Sir, it should be less than the rank of B also, because the multiplication can also be thought of as linear combination of rows of B.
Okay.
So in that case, by the same argument, the rank of AB will be less than rank of B, and since both of them are true, then I think the minimum condition comes.
Okay.
Whichever is minimum.
Okay. Anybody else? Priyanka Singh, you have also not spoken.
Yes, sir. So I think that rank of AB is less than equals to rank of A, and less than equals to rank of B.
Okay. So that is actually the right answer. So, and the reason is the following. The reasons that you guys gave are in the right direction, but this is the proper formal reason that when we talk about the rank of AB, we can talk about the column space of AB, right? And the column space of AB is actually contained in column space of A. Is that the right thing to say? Orko, can you prove that column space of AB is contained in column space of A?
If I'll think about it, sir.
Okay, think about it now, all of you. I want you guys to. Yeah, Rohan.
Yes, sir, because AB is nothing but the linear combinations of columns of A. So obviously it will be contained.
I'm saying column space of AB is contained in column space of A. Column space of AB is a linear combination of A and A into B both. So slightly, a little bit, so you're right.
Yes, sir, it will be contained
one
because
missing segment.
in the first class, I think you showed us that matrix multiplication can be viewed as the linear combination of columns of A, which is nothing but the column space of A.
Yeah, sure.
And
but
that is, yes, so therefore column space of AB has to be contained in column space of A. Like I might not be able to say it properly, but I know.
Yeah, we all know. I want you guys to write it in a more formal fashion. Okay, so column space of AB is contained in column of A. That is the proof. Okay, because the column space of AB is contained in column of A, therefore the dimension of AB, space of AB, has to be less than or equal to dimension of A. Right. Similarly, column space of AB transpose, right, is contained in column space of B transpose. Similar thing, right? Okay, उसके कारण column space of उसके कारण rank of AB is also less than rank of B, because rank of AB is nothing but rank of column space of AB transpose, right? We just saw this here. You see, the column space of A and column space of A transpose both had the same rank, both had the same dimension, right? Similarly, in this case also. So same argument goes, just that you have to slightly go back and convince yourself that this is the case. Okay, please convince yourself. All right. Okay, so anyway, just remember this. second question that I don't want you to answer right now is this, which will be actually very useful. Rank of A transpose is actually equal to, not less than equal to rank of A. Okay? And similarly, rank of A transpose A is equal to again rank of A. By the way, rank of A and rank of A transpose are same, right? You guys agree to that?
Yes, sir.
Right? ये तो हमने बार-बार देखा है कि rank of A और rank of A transpose same होंगे, right? Now I'm actually taking B as A transpose here and saying that, hey, you know, this less than equal to thing actually becomes equal to thing. Now this is exactly, Rohan, where that contained argument has to be written in a very, very rigorous fashion, so that you see that actually A transpose column space and A column space are actually identical. They're same, and therefore the ranks are same. Okay, Rohan?
Yes, sir. Yes, sir.
So batao, Arko, you thought about it?
Even for this, then we can say the same thing, that it is a linear combination of, again, the columns.
So
it is again, A will be A transpose will be contained in the subspace in the column space of A.
And A will also be contained in the column space of A transpose. Why? Both the sides. Actually, in this case, both the sides will come. In fact, here is another argument that A transpose have the same null space. Other way to prove it.
So by rank nullity theorem.
Yes. Yes. Right. Another way to think about it. Okay. So again, guys, as I said, this is not a linear algebra class. You know, I wish I could just like spend the whole semester on this, but it is just not possible because this is not a linear algebra class. And so a lot of homework has to be done from your side so that you get the, you get the LA, you nail it basically. Okay. So I'm again requesting you to go back and solve these questions yourself. Take the book and solve more questions from the book. This is the only way to learn linear algebra. You can't, I mean, if you just hear and do nothing about it, it will absolutely disappear in 2 weeks. Okay, so please be under no impression that just attending the class is enough. No, it's not. Okay, just to give you a brief, just to give you context, the amount of preparation of linear algebra I have to do even after teaching like 4 or 5 times all these stuff, okay, in my life, I still have to do like 3-4 hours of preparation because I also forget everything. Okay, I mean, not that I'm any great, but I'm not bad either, right? Which means that some of you may be of my level, if not all of you. Most of you will be better, but some of you will be of my level. And for those who are of my level, I'm telling you that you have to prepare a lot. Okay, so again, you go back and revise all these things and solve a lot of questions on these. That is the only way to learn this. There is no other way. Okay, so I'm just stopping here, and I'll just go to the final topic of the day. I mean, we did